We'll do a brief recap, as I'd like to do typically. Good. So what we're going to talk about tonight is uh, I want to really stick to the most essential ideas. So we spent quite a bit of time with the photoelectric effect last time, and that's really important. So the photoelectric effect, to be honest, is one of the two um, ideas that Albert Einstein won a Nobel Prize for in physics. And it's kind of interesting to me, too, because out of all the work that Einstein did with grand unification theory and all those things, and that was never like officially recognized, just the photoelectric effect, which he did out on like the back of an envelope or something. And and Brownian motion, which was an explanation about how you could actually see molecular motion through a microscope. And but aside from that, like all the relativity stuff, nothing. It's kind of strange. Anyway, I digress. So what we're going to do tonight is we're going to talk about wave nature matter. Early models, not going to spend too much time on it because they're not good. And then we are going to talk about atomic spectra and the Bohr model and de Broglie, which is something that you should know about. This is probably the first time de Broglie won a Nobel Prize in physics based on a PhD dissertation, and that has only happened once. So that's pretty cool. All right, let's go a little bit faster. So we talked about early understandings about particles, and black body radiation. The significance of this is it's the first time that temperature and therefore energy was related to wavelength. And then this is results from experiments that my students had done in previous semesters, where we took a look at the current and voltage characteristics of LEDs. And you can see that voltage is on the left-hand axis. And there's definitely a correlation between color and the sort of threshold voltage at which they begin producing light, because LEDs are like the photoelectric effect in reverse. So more evidence about the connection between wavelength, frequency, and energy. And so if you plot those concepts I was talking about, you actually get a straight line, and the straight line turns out to have a slope equal to Planck's constant. So this is the so-called quantum hypothesis, that the smallest units of energy can actually be transmitted by particles called photons, and the energy that each photon carries is directly proportional to its frequency. And that proportionality constant is called Planck's constant. And we have it in two different forms. In the examples I did last time, I prefer the one that's in electron volt seconds, because we're usually talking about very small quantities of energy anyway, and stuff that electrons are doing. So it does kind of make sense to use the constant that is in electron volts. So it's kind of weird. How can something that has a wavelength also be, quantized, be discrete, because we picture waves as being infinite. And I talked about how you can actually use math to create localized wave packets. It's kind of cool. It happens by using harmonics at different amplitudes. So we went through the photoelectric effect in quite a lot of detail. But the interesting thing is that the photoelectric effect represents an interaction between light particles and electrons. And light, if it's at the right frequency, can actually ionize electrons. And that's really what the photoelectric effect is all about. If you've ever left something out in the sun for a long time and it fades, that's exactly what's going on. But if a photon is going to have an interaction with a particle that we know has mass, that implies that the photon also has momentum. So this is an interesting result that you should kind of sort of hang on to. P in this case is momentum, and it's Planck's constant divided by the wavelength. So if that's the case, then that means that what if the energy of the photon is not big enough to ionize the electron? What if it's, a lower energy can sort of like ring the bell, so to speak? So we definitely see situations where photons can wind up having the momentum being involved in collisions. So this shows this is actually a very high energy of photon. resulting in the production of an electron and its antiparticle, positron. Here's the example of what it looks like in a bubble chamber. A bubble chamber, I included a picture of it on the right, sort of a stylized picture. And again, speaking of things that were worked out on cocktail napkins, two physicists walk into a bar and they order a couple of beers, and they notice the bubbles are rising inside their beer glasses, and they start talking about, hey, you know, what triggers those bubbles? And if we wanted to see evidence of charged particles, maybe we could get particles to go through and make bubbles. And that's essentially how it started. So you have super cold, you have liquid nitrogen essentially, and you expand the liquid nitrogen so it's ready to bubble, or cavitate is another word for it. And a charged particle comes in, and, or actually a photon comes in and goes through this particle antiparticle production, and then we see the curls because they're in a magnetic field. And the curls, one's clockwise, one's counterclockwise, because we have a positively charged particle and a negative one. So what's the deal then? Is it a wave or is it a particle? And of course the answer is yes, it's both. So complementarity states that light particles, photons, have wave-like properties and also have particle-like properties. And if that's the case, then maybe everything has wave properties. So we actually see this happen, the wave nature of matter. And this is possibly a conceptual question. So if you'd like to put asterisks next to something, this is a good one. And it shows that if you just rearrange that formula we looked at before, that anything that has momentum could also have a wavelength. But you're not going to observe the wavelength unless you have diffraction grating, which is not something that we talked about earlier. That's in chapter 24 of physical optics is what it's called. So in order to detect the wavelength property, then you have to have an interaction with something that is on the order of the size of the wavelength anyway. And so these wavelengths are going to be incredibly small, because as soon as something has a significant momentum, that momentum is in the denominator. So that's going to make everything really small. But particles have been, the wave nature of electrons has been observed because their momentum is really small. So early models, this is a plum pudding. You probably saw all this before in chemistry. And Rutherford's experiment really shed some light on what we're talking about. So Rutherford's experiment involved alpha particles, which are just helium nuclei, essentially, and stripped of electrons, so they have a charge of +2. And hitting a metal foil, hammered out really, really, really thin, or rolled, or however it's done, down to about 10,000 atoms thick. And so gold is just about the only material we can get to become that thin, at least in Rutherford's time. We could get mylar to be that thin also. So essentially Rutherford's experiment showed that when he fired these helium nuclei, I'll go back one, when these helium nuclei were fired in the metal foil, most of them just went straight through. And he had a viewing screen that would fluoresce when these alpha particles hit it. So he had a couple of graduate students, because the flashes aren't very bright and you had to view them with a microscope. And it made sense to do this at night so you could see the thing. So he had graduate students staying up all night counting little tiny flashes. Yeah, that's what graduate students are for. But they got kind of tired of that and figured out a way to actually measure them audibly with clicks. And their names were Geiger and Marsden, and the name of their invention was called the Geiger counter. I don't know why it's not the Geiger-Marsden counter. I think it probably was the Geiger-Marsden counter, but it's just too hard to say. So anyway, our current model is that the atom is mostly empty space, but this is kind of a joke because this is clearly not to scale. The difference between the size of the nucleus and the size of an electron's orbit is 5 powers of 10 different. So what do we know? Well, again, we kind of look at evidence from a historical point of view. People are getting pretty good at making different kinds of light. So these discharge tubes, you've probably seen them before. They're essentially neon lights. That's the idea. So it's light created with high voltage. And as electrons work their way through the gas, then they stimulate the electrons that are part of the gas molecules. And as they're stimulated, their electrons go to a higher energy level, and as they cascade down, they release light. So one of the things that was observed is that with gas discharge tubes like this, that instead of, when you take a look at the light they produce, the light actually is only a handful of frequencies. So what I'm showing here are two different kinds of gas. If I had to guess at this, your textbook could tell you which one of these are. So the bottom one is the absorption spectra of the sun. This is more like a continuous spectrum. But the light that we get from neon lights is actually a discrete spectrum. We only get certain wavelengths out. So a lot of work was done, particularly around hydrogen, to try and figure out its spectrum. And it looked like there was sort of, if you wrote down the wavelengths, what exactly the wavelengths are, it seemed like they followed some kind of pattern. But this is not really an explanatory model. It's more like an observational model. So it doesn't really explain why. It just says, well, this model sort of predicts what we're going to see for wavelengths. And there are different models for this. Again, we're talking about hydrogen, different models for visible spectra, ultraviolet, and infrared. So here's what we have. And this is really significant. So I want you to slow down and think about this part. Again, this is a good fodder for a conceptual question, is when we talk about the different wavelengths that are produced by hydrogen, you can see they definitely seem to come in discrete sets. And we have the infrared, which is going to be in general weaker photons, and the UV, which are going to be the stronger photons. And the shortest wavelength of light that hydrogen can produce is 91 nanometers. That's important. And I'll show you why in just a few slides. So Niels Bohr was the first person to pose the question that, well, we sort of have this planetary model where electrons are in orbit around the nucleus, but that doesn't really work because planets can occupy different orbits based on their energy. And that doesn't make sense in a quantized world. So maybe only certain orbits are possible. And it also made sense that if only certain orbits are possible, then there would be additional sort of quantum numbers, if you will. So we have the base quantum number, and then also if only certain orbits are permitted, then that means the angular momentum also has to be quantized. If you get more into it, that's super important. But at this level, it's more kind of observational, yeah. So here we go. If only certain orbits are allowed, it still has to obey Coulomb's law, right? So we have a positively charged nucleus and a negatively charged electron, and there's a force that keeps the electron in an orbit. So when we take a look at this and apply the spectrum that we've seen, the implication is that 91 nanometers corresponds to an energy level of 13.6 electron volts. So remember how, let's see, I'm going to switch to my document camera here just for a second. Let's see if I can do it on the fly. And I think I have to open my document camera. Where are you? No, that's not it. Shoot. Okay, I'll get there in a second. Somebody just tell me right now, what are you looking at? Do you see a whiteboard, or do you see my screen?
We
Still
see
see your
your
screen.
screen.
Okay. So I heard my screen. Okay.
We actually, where did this go? Shoot. Yeah, so if you're like in full screen mode and you have on the right-hand side that little drop-down menu with all the videos,
Yeah.
in the upper right-hand corner, there's like a little screen with a smaller screen in it for us. If we click that, that will swap the screens for us. And so we can make your small screen that is a whiteboard the large screen that we're seeing. I don't know if that will work for you, but I just found that on my side.
That's cool. All right. Let's see.
So you wouldn't have to switch is what I mean, if we could all make that happen somehow.
Right. Okay. Well, if you can see my whiteboard, I just wanted to do something really quick. We'll be more careful later on. I'm just going to do a quick test here. Is that, whoops, wrong pen. So does this look like the capital letter E? Can you see it?
Can you
down a
move
little
it down?
Whoop. Better?
Mucho gusto.
Okay. Anyway, if we take the Planck hypothesis, E equals HF, which is also HC over lambda. And then if you put in 91 nanometers here, you get a number 13.6. So I'm going to go back to my notes. And then talk about this diagram. So we have the principal quantum number n, and n equals 1 would be what we call the ground state. So if you have a photon that comes along and has an energy of 13.6 electron volts, that's going to ionize the ground state. It's going to be out of here. We have an energy level diagram over here, and the dotted line up here talks about ionization energy. So the idea with an energy diagram like this is that any electron that exists with an energy level above this, a positive number, is not in a bound state anymore. It's in a free state. And these energy levels represent the potential energy required to eject the electron from that particular location. So if we have a photon that's in n equals 2 state and if an electron is in n equals 2 state, gets hit with a photon with an energy of 3.4 EVs, you add them together, total energy is 0. That electron is out of here. Excuse me.
Out of here and assumingly like joining into something else or what?
Yeah, going off to, electron summer camp or whatever they do. So, yeah. So the more important thing for us, though, is because concepts about ionizing energy were understood pretty well. And, right, I know, only 10 minutes left. We got the cheap version. So the the more important idea are transitions between principal quantum numbers. So if we have a photon that comes along that's got an energy level that's equal to the difference between n equals 1 and n equals 2, the electron won't be ionized. It'll just be in an excited state. Good for you, electron. So, and the same is true with all the others, but the electron's going to spend most of its say, remember, this is just hydrogen. So 1 proton, 1 electron. It gets way more complicated when you have more electrons. So in grad school, I was doing research on yttrium YAG laser, which had 47 electrons. It was a lot to keep track of. But one of them lased, which was cool. Anyway, as we move forward, then it turns out that these start to explain what the spectra for hydrogen actually looks like. So if you remember those weird series that we had before, like some of them involved numbers, if pardon me, but I'm just going to zip back. We had these weird things where, oh, here n equals 2, 3, 4, and so on. Here n equals 4, blah, blah, blah. This is for ultraviolet. This is for infrared. And I'm guessing the previous one started off with a 3. Yo, okay, that makes sense. All right. So the Lyman series, the ultraviolet, are transitions from the ground state. And visible are transitions from n equals 2. And these are all transitions from n equals 3.
So this is implying that like you can't see anything unless the electron is ionized.
Well, okay, so here's the main idea. Electrons can exist in different energy levels, and I'm just going to go right here. Electrons can exist in different energy levels, and it's in transitions when there's an interaction with a photon. So that means that this interaction with an electron can go one of two ways. You can have a packet of energy that comes in with a photon, and if it's the right match, it can transition an electron to a higher energy level. So that's absorption. But eventually, the electron is probably going to drop down to its either an intermediate state or all the way down to the ground state. And that's emission. So that's the mechanism for interaction of atoms with light. They either absorb photons, but it has to be just the right photon, or they emit photons. And that'll happen because of an energy transition. So this is a great diagram. It shows how the different series are broken up. So this is a big jump. So the jump from n equals 2 down to n equals 1 is a big one. That's a lot of energy. That's why it's ultraviolet. And all these others are also going to be ultraviolet. But you can see that the difference in energy level between 2 to 1 or 3 to 1, it's not that much. And in fact, the difference in energy levels from like 5 down to 1 or 6 down to 1, it's almost the same thing. So that kind of explains how the spectra for hydrogen comes in sort of bunches, clusters. So the Lyman series, again, this is ultraviolet. Here, this is a more moderate energy jump. So it involves transitions from n equals 2 to higher states, that's absorption, or higher states down to n equals 2, that's emission, and that's visible light. And of course, the transitions to n equals 3 are very low energies, so those are going to be ultraviolet. How are we doing on that? Just any questions? Okay, good. So we have, yes, go ahead.
Oh, I just said good.
Okay, thanks. We have about 5 minutes left, so I'm going to just go a little bit quickly. And I think what I'm probably going to do is I will post a couple of practice problems, and they'll be separate videos. So I was fortunate last time I was able to use a free upgrade and record a longer lecture last time, but we are clock's ticking. So here we go. The de Broglie hypothesis was that, and this is kind of an interesting aside, that his idea was like, wait a minute, if only certain orbits are quantized, and if you remember from physics 1, we had a concept called resonance that involves standing waves. So his hypothesis is that these, maybe really the electrons were, if they're also have wave-like properties, maybe they're sort of like standing waves. And that's how come only certain electrons are possible. So here's our n equals 2 state. And you can see if we count wavelengths, the dotted line just shows an oscillation of the wave back and forth. But if we count them up, so go from crest to crest. So this is a trough, a crest, and a trough. So this is 2 wavelengths here. And then this, so trough, crest, that's 1, trough, crest, 2, trough, crest, that's 3. This is 3 wavelengths. And so that was a connection that de Broglie was thinking about. But he was, he was a doctoral candidate. And so his advisor said, yeah, we got to call somebody else in to take a look at this thesis because we don't know. So as you can see in the slide, they called in somebody named Albert Einstein. And Einstein was like, yeah, makes sense, sounds good. And then went out for coffee. So yeah, there we go. So we finally got to a summary. What are the big hits? Number one, the quantum hypothesis. That's essential. And then wave-particle duality is very significant. And so all matter comes in wavelengths. But the trick is that if you're going to find the wavelength property of something that has mass, then it's going to be, it has to be something that's very, very small. The wavelength of electrons is very, very small. So it's been noticed to create diffraction in crystals, which is the main way it's been determined. So you all have a wavelength too, but it's super small and it's hard for you to be able to see it. And then finally we get to these energy transitions, and that's the third big idea that comes out of this, is that the interaction of light with matter has to do with electrons changing orbital levels, and they go up when they absorb and they go down when they emit. So actually, let's just start another Zoom meeting, because I think I can do that pretty quickly, and then we'll do a couple of examples, and that'll give you the opportunity to try an example too. All right, so just get into Canvas, and I'm gonna stop this one. Oh, shoot. It's gonna probably take 4 minutes or so for this thing to record. So I'm gonna set up another meeting, and you can go like get a snack or something like that. Dina, whatever you were eating looked really good. So,
thank you.
so 6:45, okay? All right, see you in a bit.